this is supposed to be, usually it's like done on a whiteboard, so I would have like lecture notes, and I would be giving a lecture, at least in the standard format. I can't do that today for obvious reasons, so I'm going to do my best to supplement with some outside materials, this PowerPoint, and I've got a online whiteboard that I might do a few derivations on if we get the chance. So, welcome to my excellent adventure. My name is Charles Cardot. We're going to be talking today about the physics of X-ray diffraction spectroscopy. So, a lot of this material is pulled straight out of the solid state physics course. So, if you want to learn more about anything that I talk about today, or you want to call me out on my fake-ass derivations, you can do it by taking that course and suffering through Morrigal and then coming back and talking to me in 2 years' time. So, what do we use X-ray diffraction spectroscopy for? It's primarily done to identify different kinds of materials, specifically materials that have periodic systems, but it can be used in some circumstances for identifying certain atomic and molecular structures. Specifically, the fact that it's X-ray diffraction means that it's very high energy, and that means that our energy is usually too large to be completely absorbed into the system. So that's good for us because it means that our X-rays, our photons, actually bounce off of the materials that we're trying to hit instead of being absorbed and done away with. So the whole goal of X-ray diffraction as a science is usually to characterize materials, and that's a bit what we're going to be talking about today. And first off, we know that if you want to characterize materials, you want to look at crystals. So crystals are very powerful because if you combine your astrological sign with your crystal healing figure, you can use it to regulate your mood, and you can gain enlightenment. And I highly recommend that you read all of these books. I get no kickbacks from them whatsoever, but you will have to use my Amazon affiliate link to be able to purchase them.
Dr. Morgul covered this for about a few weeks.
Oh yeah, you missed out on that part. This is a highly scientific fact. No, I'm kidding. We're going to talk about real crystals. So, if you want to understand, I know, boring, right? So, if you want to understand how X-ray diffraction works with periodic systems, you first have to understand the periodic systems themselves. So, there are a lot of different things that can be considered crystals, and it's not just minerals and metals and that kind of stuff. It can be proteins. Proteins can form into crystals. You can even have things such as liquid crystals, which move as a liquid but still have orientations that resemble crystal structures. So we've got a couple examples here. Our simplest is salt, which is just NaCl. That's a real basic cubic boy up there. Technically, it's a face-centered cubic, but it just looks like a cube in this picture. I have a dog running around my basement, and she just hit the door. Okay, good for her. Then we have a couple other examples. They can take other forms, other structures. This is also technically face-centered cubic, but as you can see, it's not as simple as salt. There's some other business going on kind of in between. And then, of course, we've got a couple other images of just general periodic structures. So what does it mean for something to be a crystal? Well, first off, it has to be highly ordered, and some might say that it must be completely ordered, but not necessarily. Often in real life, we find crystals that have defects and certain strain factors that cause them to be not perfectly periodic. But they must also, in general, at least in theory, have a single repeating pattern which defines them entirely. So a couple examples of this, you could have, a cube that's repeated over and over. You could have a hexagon that's repeated over and over. But this can be also like a 1D shape, 2D shape, 3D shape, whatever dimension you're working in. It just has to be some sort of shape in that dimension. Well, there's only really one option in 1D. It's just a line. But in 2D and 3D, whatever the shape that you're using is must be repeatable by translation exclusively. So you can't translate and then rotate it. It has to be only by translation. So this is defined more rigorously in terms of Bravais lattices, which are a very powerful way to systematically and uniquely characterize different crystal structures. So it's a Bravais lattice. First off, this is Auguste Bravais, a very famous and very sexy French physicist who did a lot of condensed matter in crystallography. You're going to find that a lot of French physicists actually were involved in crystallography, which is why I personally decided to get into it. Yeah, got to go after my own heart. But we use Bravais lattices as a way to kind of characterize what is and is not considered a lattice specifically. Now, crystals are not necessarily made up of Bravais lattices, but in general, you can use a Bravais lattice to describe any crystal. And we're going to get into that in a lot more detail later on. So first off, a Bravais lattice is basically an infinite set of discrete points which define your crystal structure effectively, and they're generated by a discrete set, or by a set of discrete translation operations, and described in 3 dimensions by this equation, where you have n, which is some integer, and then a1, a2, and a3, which are some primitive vectors. So these primitive vectors are going to define what's known as a primitive unit cell, and we're going to get into unit cells in a moment. I'm going to give you guys a quick example as we move over here. So if you... Hold on. Work with me here. Okay. Ignore that. That was me practicing. So I'm going to draw the same structure again, I promise. So if you have a structure of some sort, and you want to figure out if it qualifies as a Bravais lattice, or even if it qualifies as a crystal for that matter, I'm going to just draw a couple points here as an example. Fill these in, so these are squares. Just pretend they're all the same length.
I don't see you.
I don't.
Oh shit, you don't see me drawing?
No.
Yeah.
Oh,
There you go.
Oh wait, now you... Do you still see it?
Yeah, we can see it now.
Yeah, I can see it.
Huh, weird, okay. Okay, good. So, let me finish drawing this. So, as you can see, I'm sort of repeating a certain structure over and over again. And it's obviously a square. We're going to call this side A, and we're going to call this side A, so that way you can see that it is the same length on both sides. So if we wanted to define if this was a crystal, we would first go back and look at our definition of a crystal. Is it highly ordered? Well, yes, it in general seems to have points that are at set distances apart from each other, and it seems to follow a pretty regular pattern. And then also, specifically, is it defined by a single repeating pattern? And I mean, to be honest, this isn't the most rigorous definition for a crystal, but it's the one we're going to be using for this presentation. So yes, it is defined by a single repeating pattern, and it's a square. And you could take this pattern and only by translation move it over and over and over again, and you could keep recreating this crystal all the way off into infinity for the rest of the time. Now, if I was to draw something like a triangle, and I was to call this my lattice vectors, this would not technically, or this would not be a crystal, because if I wanted to make some system out of this shape, I would have to rotate it every time. So I have to take this, and then I would have to turn it on its side, so that way it fit in here, and then I would have to turn this on its side, so that way it fit in here, and so on. And then I would get a square, and then I could repeat that off into infinity. But this would not be considered a Bravais lattice. So because this is in 2D, we can define this as simply in the 2D case, where Rn is equal to 1 A1 plus, sorry for the slow writing, A2. Where A1 and A2 are primitive lattice vectors, where in this case we could define A1 to be along, we said this is, say, X, Y for simplicity, and then gosh, I can't draw for crap. A2. Alright, this is A1, and this is A2. So, using this equation for your Bravais lattice, you could reach every single point on this lattice simply by translations, or by, in this case, using integer values of n1 and n2. Z is all integers, right? Yes. Okay. So you could also go negative if you wanted. You could have negative n1 or negative n2, and you could go in the opposite direction. It doesn't matter what point you start at. You could basically start at any point in this crystal lattice, and you could say, I can start here, and by using linear combinations of my two primitive lattice vectors and integer values of n1 and n2, I could reach any other point on the lattice. And that's effectively the main definition of a Bravais lattice, is that it has that discrete translational symmetry. So I also mentioned primitive vectors. So primitive vectors are used to define what's known as a primitive unit cell. And in this case, the simplest primitive unit cell is a square. So if I have an atom on every corner of the square, the main definition of a primitive unit cell is that it contains only one lattice point. So a lattice point there's a couple different definitions, but the easiest way for me to think about it is a single atom. So it's kind of difficult to see based on what I've drawn, but if you were to pretend each of these was a perfect circle, you would be taking out 1/4 of every single atom, and this would add up to a total of 1 lattice point inside of here. So another example of this is if you kind of had a orthorhombic shape like this, and I drew a circle here, I drew a circle here, and I drew a circle here, drew another circle. And you were to see which fraction, and you were to add up all the fractions of the circles inside of that these lines bisect, you would also come up with a single lattice point of 1. So an example of a crystal structure where you don't have a Bravais lattice, but it is still a periodic lattice, would be if you had an atom in the middle, and then you were to do the same thing where you try to see if these primitive lattice vectors only had 1 lattice point inside of them. You would have 1/4, 1/4, 1/4, 1/4, and then 1. So this would come up to a sum total of 2, which means that technically these are not the primitive lattice vectors which you could use to describe this structure. So the unit cell is basically whatever region of space that you're using to repeat over and over again. And you could do it perfectly without rotation, just purely by translation. So that's how we would make a Bravais lattice. And you can basically see that you're pretty limited in this sense. You can really only have some type of parallelogram. So in this case, A1 and A2 are the lattice vectors, and they would define something pretty close to what we have here, in sort of orthorhombic shape. So another thing to note is that, as I said, you're pretty limited in your choice of Bravais lattices. You only ever have 5 possible Bravais lattices, and they're almost all identical. The first one is the one we were talking about earlier. This is called monoclinic, where the length of A and B, which we were really just calling A1 and A2 earlier, but the length in A and B are not the same, and then the angle between them is not equal to 90 degrees. And then this is the situation I described earlier, where there was one in the middle, and they're kind of showing you how this might, at first glance, because it's cube, it just looks like a square, you might assume that it's a primitive lattice, but because it contains more than 1 lattice point, these 2 vectors don't actually define the primitive lattice vectors for it, and you would instead arrange them in this kind of form, where they have some angle between them, and the length of the 2 lattice vectors, in this case they're calling them C and D, are equal to each other. And then there are a few other ones. This one is the dumbest in my opinion. A equals B, but theta just happens to be a very particular value. And then this is usually the simplest one, the square one. So because there are only 5 possible Bravais lattices, we'll get to a moment. We'll get to why they're so important later on. But another thing that you should note about them is that the primitive cell is not necessarily unique. You can define a lot of different lattice vectors that you can use to make a primitive cell. So basically, these, as I said, they're all just parallelograms. None of them are unique. As the only restriction is that they only contain 1 lattice site. So in this one, like you can see, it's this weird, wacky shape. But if you were to sum up all of the fractions of each atom that is contained within it, you would only get 1 lattice. You would only get 1 full atom contained within the area of this structure. And a simple trick which I learned earlier is if you have, let me move over here. If you have a lattice which appears to be kind of a bizarre structure, and you're not certain if the lattice vectors which someone's showing you are primitive lattice vectors. So here, okay, this is. Give me a moment, actually. I'm going to draw something more dramatic. Okay, that's a big one. Okay. So let's say it's like this. How am I going to do this? Okay. Wait. Yeah, okay, this works. And say you're not totally certain that this defines a primitive lattice vector. You can take this whole structure and just shift it up slightly. So you literally just take this same thing, draw it again, and now ask yourself if it contains a single atom. And in this case, I've shifted up. I'm outside of the range of these 3 atoms, and inside the area of this shape, I only have 1 atom. So that's a pretty easy way to kind of confirm if something is a Bravais lattice or not. or sorry, if something is a primitive unit cell or not. Pardon me. Bravais lattices are defined by primitive unit cells. There we go. So there, you can use Bravais lattice. The reason that Bravais lattices are so powerful is that you can use them to describe any periodic structure in the world. If it's periodic, a Bravais lattice can describe it. And in 2 dimensions, there are only 5 of them. So based off of these 5, let me go back one more. Based off of these 5 structures, you can describe any lattice that you encounter. So what we call the fakers are, and to be clear, there's some terminology variation between fields. So in physics, and specifically in crystallography, a lattice usually refers strictly to a Bravais lattice. But, and Aaron, this is the part where you need to start correcting me if I start messing up, okay? So this is on you. So, and outside of physics, sometimes in material science and other places, a lattice just refers to any periodic structure. So, for example, this is something known as a Kagame lattice, but technically, based on its structure, you can't define a primitive unit cell which only contains 1 atom or 1 lattice point. So this isn't technically a Bravais lattice. But you can kind of see what I'm talking about here. If you look at a periodic structure, in this case, a Kagame lattice is also a periodic structure. But this periodic structure is made up of a bunch of armadillos, and they're all arranged in a periodic way. So we can definitely say this is a periodic structure. You could say this is a crystal. But it's defined in terms of a lattice, which are the points, and then some repeating object, which takes place in those points. So this is what's known as a periodic structure can be defined as a lattice convoluted with a motif. So not every periodic structure is a lattice, but if the motif is just the atom, then in that case it is a Bravais lattice, but in this case our motif is some armadillos. A more complicated example, as I was saying earlier, is the Kagame lattice. If you were to take this shape and then put it in this format, you could take this picture that you have here, just ignore everything else around it, and take this picture that you have here, and you could take it in like a rubber stamp, and only using translations, you could recreate this entire Kagame lattice. And it's a little bit hard when you first look at it, and you might even have to take it and try it yourself, but you can take my word for it for now that you could take this whole thing and just repeat it over and over again and recreate this Kagame lattice. And the thing is, this shape might look familiar to you because we not only drew it earlier, but we also defined it back in our 5 possible Bravais lattices as our monoclinic Bravais lattice. So by using a monoclinic Bravais lattice, along with a motif, which is this kind of triangle shape in the center of it, you can define an entire periodic structure in terms of the Bravais lattice convoluted with the motif, where in this case, every unit cell of the Bravais lattice, inside of it, you just put the motif, which is this kind of triangular structure. So this can be done for any 2D or 3D system. Really quickly, in 2D, there are 5 Bravais lattices, 5 possible Bravais lattices. In 3D, there are 14 possible Bravais lattices. And those, some of the common ones you might have heard of are cubic, body-centered cubic, and face-centered cubic. If you've taken intro chem at any point, then you've probably run into these guys before. They're pretty common. So now that we have an understanding of the possible kinds of crystal structures that can exist out there, we also want to understand, well, what does X-ray diffraction with those structures look like? So our main goal is to kind of understand how X-ray diffraction works and how it diffracts off the periodic structures that we've defined so far. That means that we need to know how X-rays, which is basically just, high energy light, how those X-rays are going to interact with our materials. So the key thing here that we're going to talk about is, or one of the key points that we want to make clear is that our X-rays are going to be undergoing elastic scattering, which means that the magnitude of the wave vector going in is going to equal the magnitude of the wave vector going out. Another way of saying this is that the energy is conserved, and this is just given by Planck's equation. So because the wavelength going in is equal to the wavelength going out, that means experimentally we can ignore all other wavelengths that we detect. So this is important because there are a lot of other wavelengths which will be present. So if you have elastic scattering, that's the ideal case. What happens more often is inelastic scattering, where there's no energy conservation, at least not in the part of the system that we're looking at. And the electrons instead go on to create other excitations, such as they can they can turn into plasmons, they could turn into magnons, they could turn into phonons, they could excite other electrons out of the system, they could undergo Compton scattering. There's tons of other things that could happen, but what we're interested in is this real thin green peak right here, right where the energy transfer is very little. So we don't want, we want, because we're looking for elastic scattering, that means that the energy transfer is 0, or at least in the experimental case, approximately 0. And that's this part that we want here. So the way that we're going to get that is, well, okay, first, we're just going to assume that everything we detect is going to be elastically scattered. Because, as I said, we only need to look at wavelength in equals wavelength out. You could have a whole other bunch of wavelengths present in your experiment, but as long as whatever wavelength you're using going in is equivalent to the wavelength that you're detecting, or at least you're only looking at the wavelengths which match the one which went in, you will only find electrons that have been elastically scattered. So that's our first condition. That's our first big important thing. Our next big important thing is Bragg's law, where Bragg's law is basically going to be our constructive interference condition. So if you have a crystal like this, hold on a moment. If you have a crystal like this one, and this is a real simple cubic shape. Well, okay, ignore it. I promise it's periodic. There we go. And you have a lattice plane, which is defined by some line. And imagine that this is, you're looking at a plane from the side. So this is technically a 3D shape, but it goes back that way. But we're only looking at a cross section of it. So you have a lattice plane, which is defined by some 2D series of atoms. And then there's another lattice plane, because the system's periodic, right under it. The distance between these lattice planes is d. Hi, puppy. And we have some sort of wavelength of light coming in. And then it's going to interact with an atom, and then it's going to come out. But the thing is, this entire sample is being bombarded with high energy light, so there's going to be light all over the place. There's going to be some that comes in and hits the very first layer, and then gets reflected back out. So we want a condition in which the light coming in, or sorry, the wavelength of the light coming in equals the wavelength of the light coming out. So that means that we can assume that the lambda on this side is equivalent to the lambda on this side. So the lambda reflected by the first lattice plane and the lambda reflected by the second lattice plane. But if you know anything about waves, you'll know that we have to deal with both constructive and deconstructive interference. So we want to be able to detect the photons that go in. I promise we do. We want to be able to detect them. For us to be able to detect them, though, we have to have a constructive interference between the light that comes in and hits this plane and the light that comes in and hits this plane. And what's going to happen is we're going to get a bunch of reflections, and if I had more space, oh wait, I can just scroll down, can't I? You could imagine that there are, nearly infinite number, at least for our purposes of lattice planes, where reflections could potentially occur, and you would get tons and tons of waves adding together. So real quick, if you have, for anyone who hasn't encountered this before, if you have two waves and you put them on top of them, and you put them on top of each other, they'll add constructively, which means that the peaks get twice as large and the troughs get twice as deep. So that's good for us, because that means that the signals that we see that are the highest are going to be the ones where we see this Bragg scattering, where we see this where we see this constructive interference. So we need to figure out what's the condition in which we observe this constructive interference. So we can assume that there's some angle theta here, and this is some height d, and you can show that through a little bit of trigonometry. This is also angle theta. All right, this is going to get tough to draw, isn't it? Oh, well, you know what? Never mind. I'm just not even going to try that. It's going to be too messy. You can show that there's also an angle theta here, and then through a little bit of trig, you can show that we will get Bragg's law pop out, which is, wait, let me make sure I don't mess this up. This is like the basic stuff. 2D sine theta. Oh wait, I have it on the other page if I do mess it up, whatever. Equals, so here's the thing. We can have, one thing about waves is that, oh boy, hold on, who's in this chat? Does anyone not know what a wave is? Or like how waves work in general in physics? All right.
Waves are when particles decide they want to be something different.
Okay. All right. We're gonna, in general, excellent dimensions are supposed to be kept pretty simple, so I'm gonna stick to it pretty simply. So waves have something known as a wavelength, which is because waves are in fact periodic as well. If you have a wave that is kind of traveling through space, you can see that the distance between peaks. Oh well, that was a. Yeah, no, that works. That works. So the distance between peaks, or between where they intersect the x-axis, or between troughs, is equal to lambda, which is whatever the distance over which they repeat is. So the thing is, if I want my peaks to match up with if I want my peaks from this wave to match up with my peaks from this wave, I have to make sure that the distance that it travels is exactly equal to an integer number of wavelengths. So that way, when it reaches this point where it's equal with this wave, the distance it travels here to here, and then it will recombine over on this side. But the distance it travels here to here, if it is not equal to an integer number of wavelengths, then the peaks won't match up perfectly, and we'll get at least partially destructive or entirely destructive interference. So we need that this distance that it travels to be equal to some integer n times the wavelength, where n equals 1, 2, 3, and so on. Okay. That's how we get Bragg's law, and it's given by the simple condition. And it's a relatively simple condition. So we know, first off, that we need for the incident wavelength to be equal to the outgoing wavelength, and we also need the angle which we interact with the sample, or the lattice planes, to be equal to, or to satisfy Bragg's law. So you can simply solve for theta, divide 2d over, take the arc sine, so on and so forth. Okay, so up next we're going to get a little bit more complicated. Reciprocal space is something that becomes very useful for us as we start to analyze periodic systems. And a really simple definition of it is, if you were just to say we have e to the I times some vector g times some vector r equals 1, where r is basically our definition of a Bravais lattice that we used earlier. The one that we had back here, this one, where r is equal to some integer times a vector plus an integer times a vector, so on and so forth, dotted with a point g which exists on a reciprocal lattice. So we don't know what g is necessarily, and we don't have to necessarily figure out where it comes from. We could if we wanted to, and if we have more time then we can go back and do that, but I'm going to rush a little bit so that way I can finish before the end. But we could figure out where g comes from, and we know that it has to satisfy this condition. So because we know what the form of r is, we can figure out what the form of g is if we assume that it is equal to some similar condition where it's an integer times a vector plus an integer times a vector. We can figure out, and we say that if this one is in terms of a1, a2, and a3, then we can define g in terms of b1, b2, and b3. And then we find that there's this relationship between all the reciprocal lattice vectors, b1, b2, and b3, and then the direct lattice vectors, or just in this case primitive lattice vectors, a1, a2, and a3. It's kind of interesting to note that a2 cross a3 is going to be normal to the plane, and then we also are dividing by what is effectively the volume, all of that multiplied by 2 pi. There's definitely some symmetry in here that we can get into more later, but basically the reciprocal lattice is just going to be another lattice which we can use, and will make some of our calculations easier down the road. So if you look over here on this graph, we see that the reciprocal lattice doesn't always necessarily match the direct lattice very well. If they're cubic, then it's the same general structure, but the reciprocal lattice vectors are not the same length as the direct lattice vectors, and if it's not cubic, if it's some sort of orthorhombic shape, then the reciprocal lattice usually ends up being something wonky or some sort of rotated or magnified form. So we want to use reciprocal lattice vectors because they're what connect us to the Miller indices. So remember what we talked about earlier with Bragg's law? We have to have planes that we can reflect these, that we can reflect our photons off of. So because we can define a family of planes in terms of something known as Miller indices. So it's a lot easier. Okay, I've got a cat and a dog who are like attacking my legs at the same time. I need like 2 seconds. Okay, I'm back. Oh, okay, so where were we? All right. Ignore everything on the right for the moment. Just look at this image. We know that, given the Bragg condition, if we have any two lattice planes, if we want there to be constructive interference and we want to be able to see some sort of photon come in and then photon come out, and we want there to be, constructive interference where we can actually detect the photon that we're using, it has to interact with a plane of atoms. So you can use the lattice vectors, which define, or specifically the primitive lattice vectors, which define where all of the atoms are within your unit cell, to figure out what planes can be made out of these atoms which are in your unit cell. So each one of these Miller indices are based off of these H, K, and L values, which come from your... So we called them M1, M2, and M3. You can relabel them as H, K, and L, which is basically where those come from. But they are also integers, and they come from the reciprocal lattice vector. And you can use them to define each of these lattice planes. And specifically, the distance between each of these lattice planes is going to be 2 pi divided by the magnitude of our G, which defines our reciprocal lattice, the same way that R defined our direct lattice. So we now have a kind of description of what the distance between the lattice planes are, which this is the one part, the D from Bragg's law. And then you can also see here, this is just salt once again. And because these are reciprocal lattice vectors, as you increase the integers, so you go up from 1 to 2, you actually, it's fractional in terms of, this is a picture in direct space. So it will be 1 over 2, which means that the lattice planes will be every half of a direct lattice vector. And that's what, okay. We'll come back to these if we have some more time as well. So we've reached about the middle. We have multiple Bravais lattices, and we know our lattices, and we know how they work. We know their structures, and we know that we're only looking for elastic scattering, which means that the energy is conserved, and because the energy is conserved, we have the same wavelength going in as the wavelength coming out. We also know that we need Bragg's law to be satisfied, and we know that it's only satisfied for certain angles. And those certain angles will give us the constructive interference that we're looking for, so we can actually detect our peaks. Now, we know that the angles are given by a combination of the wavelength and the HKL plane. So we know that the HKL defines these planes, and the distance between them is given by this formula. And we also, the other thing we need is the wavelength, which we get from whatever our experiment is. Normally we use copper K alpha, which is a very particular wavelength, which we, as physicists, understand very well. So as long as you have your wavelength and your HKL values, you can define the plane in terms of Miller indices, or in general, you can just define any plane. You can do it in direct space, but the reason that we're using reciprocal space is it will make things easier for calculating the intensity later on. But now we know what we have. All right, 1 second. Now, the questions that are remaining is, what angles are the Bragg peaks going to be at? We know we need to still solve for them. And then how big will the intensity at the Bragg peaks be? Because we need to know, effectively, we're going to have two things. We're going to have intensity versus angle. And we want to be able to recreate what we see in experiment. So the intensity will be given by something known as the structure factor, which we'll get to in a second. So the Bragg peak position, we can find this from the distance between the planes. So we have D, we solve for theta in terms of the Bragg's law, and like I said, you just take the arc sine lambda over 2D. We're going to assume that we're using only one integer number of wavelengths. You technically could have multiple, but for our purposes, our wavelengths that we're using are small enough that are of the optimal size that we're only going to get one full wavelength between both of our lattice planes. And then to find the Bragg peak intensity, we're going to come up against something known as the structure factor. Now, a rigorous derivation of this would take about 2 hours and uses Fermi's golden rule and involves a relatively complex Fourier analysis. If you want to, we can go into that afterwards, but for right now, I'm just going to have to let this be fact. So the structure factor is kind of like the probability amplitude in quantum mechanics. The structure factor, absolute value of the structure factor squared, will give you the intensity that you will see. And it's defined for some value g, which is in terms of HKL. So we'll know that for certain HKL values, which tell us where our theta values are going to be, because that's what our distance between planes is, we can figure out what the magnitude is. So the structure factor is defined in terms of a sum over all the atoms in the unit cell of first what's known as the form factor, which is basically some constant value which is calculated from the electron density of whatever atom the photon's interacting with, times some exponential, which is in terms of the reciprocal lattice and whatever lattice plane you're using. Okay, so a little bit more about the Bragg peak intensity. So we know that the X-ray form factor, this can be calculated either experimentally, or you can do some rather involved derivations involving the electron density, and you can get very into it. But it drops off rapidly as the sine of theta over over wavelength increases. So that's going to lead to a phenomenon where overall our peaks are going to be smaller at higher angles because the form factor has decreased. Okay. So we know that the structure factor is given by this equation. And if we wanted to actually calculate what the structure factor is, what the square root of the magnitude would be for a particular example, we have here chlorine cesium, which is a body-centered cubic 3D structure where we have chlorine at every corner and then one atom of cesium in the middle. So it's at the 1/2, 1/2, 1/2 position. So you could calculate this by, in this there's a few different standards. Here they use F. Back here we use S for the structure factor, but keep in mind this is just the structure factor. And as I said, it's defined for some HKL values, which are our integer reciprocal lattice coefficients. So if you wanted to calculate, for example, cesium, if you wanted to calculate, for example, what the structure factor is for this, you would first sum over all the atoms in the unit cell. Now, this is a particular point that I sort of glossed over. The atoms, if they're, in this case, if you were to represent the primitive unit cell of this, you would only have one chlorine and one cesium inside of it. So in this case, they're only summing over chlorine once and then over cesium once. So you have your form factor for chlorine, then you know that the chlorine is located at 0, 0, 0, and that means that H is 0, K is 0, L is 0, it's just E to the 2 pi 0, so this just goes to 1. And then for cesium, you have 1/2, 1/2, 1/2, so it becomes E to the I pi plus times HKL. So now we have a general form for what the structure factor is for any HKL value. So it's easiest usually to input whatever atoms you have in your unit cell, calculate them in terms of the HKL values, and then when you want to figure out what the structure factor is for this unit cell for a particular plane which you have the Bragg reflection satisfied at, then you can input your HKL values. It gets complicated quickly. Okay, so we know our peaks, we know what angles they're at, now we can finally start measuring crap. First of all, we have the intensity, which comes from the structure factor, and then we have the angle, which comes from Bragg's coefficient, from Bragg's law. So this is just an example for zirconium, which is a hexagonal unit cell, and for the 1, 0, 0, which is H equals 1, K equals 0, L equals 0, we have a peak at about 37, and then it has a small intensity, and you can see that for each one of these peaks, they're all associated with some particular with some particular lattice plane. And if we go back here and you look at them, there are lots of lattice planes, and you could have graphs like the one we were just looking at that are absolutely full of peaks. It all depends on the spacing between each of these lattice planes and how long each of the primitive unit vectors are. So this is kind of what our results will look like, and now we can get into actually running experiments. How much time do I have left? I have a clock right here. Never mind. Oh, I'm not even in presentation mode. Why didn't you guys tell me? Well, listen, I'm doing my best.
You're doing great.
Thanks.
Doing great.
Okay. So when we actually want to run an experiment with this, now that we have an idea of where we should see peaks and how large those peaks should be, we can develop a couple different experimental apparatuses. Technically, there are lots, but there are a few that are used in particular circumstances for different types of crystals and different geometries. A very simple one is kind of the one shown in this upper left-hand corner, where you have some source of X-rays. Those X-rays are collimated, so that way they're all kind of coming out in a single straight beam, and they're all parallel to each other. It interacts with some sample that's at some set angle with reference to the X-ray source, and then those X-rays experience Bragg reflection. They enter another angle limit, another collimator of some sort, which then interacts with a monochromator. This filters out all the wavelengths which are not equal to the X-ray source's wavelength, so it's tuned very specifically to whatever X-ray source you're using, and this makes sure that you only are sampling wavelengths that are equal to the wavelength you started with, and then those are fed into a counting detector, which basically is a pretty rudimentary way of detecting the intensity. The angles at which you have more counts is where you have more intensity. So this can also be modified into what is kind of a spherical sort of apparatus, where this is what's known as a Laue machine, or at least I believe it's called the Laue machine. Yes. Yes, this is a Laue machine. So same general setup. You have an X-ray which travels through some sort of collimator or some sort of slit, which makes sure that they're all traveling generally straight, interacts with the crystal, and then in this case the crystal is not some 2D shape, it's some large 3D structure, and it's going to interact in multiple different ways inside of the it's going to basically get scattered inside of the crystal, and then when they all come out, they're all going to fly off at various angles. But the thing is, because they've been scattered in here, the only ones that survive are the ones which experience Bragg reflection, because those are the only ones which are going to experience constructive interference. Then there's a shield here, because in general, this beam, there will be lots of X-rays which don't actually interact at all, but the ones that do interact will be scattered at some angle, but the ones that don't interact will just hit the shield. So we have a little bit of a blind spot in the middle, but in general, you'll see patterns start to emerge, and we can look at some pictures of what. Actually, yeah, I can pull them up really quick. Allow me spectroscopy. I'm pretty sure. Oh, well, that's just the same picture that we had earlier. Now this is kind of this is sort of some data that someone has, and you can see that they will all start to diffract at certain angles. They don't really have it. It's kind of annoying in this picture. It just looks kind of random, but whatever. You should be able to see patterns start to form, and the distance between these can be measured, and you can infer information about the structure of the crystal from it. And then there is another type of symmetry experiment, which is known as Debye-Scherer symmetry. This is primarily what I use. It is really ideal for powder. So a kind of, and this is kind of another angle view of this similar system. But there is a phenomenon, or not a phenomenon, there's basically a problem with growing large crystals. So this case up here, where you have a big crystal, is pretty rare, and it's very difficult to grow large samples of a single crystal. So what happens is we often kind of make a really crappy version of the crystal where there's like just tiny, like 10 nanometer long samples of it, and instead of trying to like align that 10 nanometer sample, we just grind it up and we turn it into a powder. So you have a bunch of crystal flecks all in this powder, which is kind of what these flecks here are shown as. And you take all of those, you pack them down, and you put that in front of a beam of X-rays. So at first you might think, all right, well, all those crystal flecks are organized randomly. There's no way that you would be able to actually align it properly with a crystal. You would actually be able to align it properly with an X-ray. But the thing is, you have the you have the luck of randomness on your side in a way. So it's a little bit hard to see in this. I think I'm going to go to the website where I got this image from. And it explains it a little bit easier here. So because all of these crystals are randomly oriented, you will have some that happen to be perfectly oriented for a certain plane of reflection. So there's a beam that comes in, it gets diffracted out, and there's a few crystals that just happen to be perfectly oriented with that particular diffraction. And the thing is, though, not all of them are going to be, you gotta kind of think about this in a 3D sense, not all of them are going to be diffracting it towards the same point. Because they're all sort of oriented differently from each other, they're going to diffract it in a cone, and you'll actually be able to use sort of a conical geometry where you start at the center, and as you move outwards, the farther away you move from the center, the larger 2 theta you're measuring. And when you see these rings, one ring will be associated with a particular, in this case they're calling it D1, but some D plane that is present within your crystal structure. And then as you get farther away, you might encounter another set of like just a few crystals that all happen to be oriented in another particular direction, where you will reach another ring that is associated with that particular plane. And the thing is, what's so powerful about this is it relies on Bragg's law, because in theory, everything would be reflecting off and interfering with each other. But the thing is, the only ones which actually survive, we know that the rings, when we see something on a ring, we know that it has to be from Bragg's law, which means that it has to be encountering some sort of D-plane. And we can use that fact to eliminate basically any sort of interference or any sort of misalignment properties. So you can still basically use powder diffraction to do X-ray diffraction and do it successfully and relatively efficiently. There are a few drawbacks, though, with this method, and we'll get to those in a second. So some of the issues with powders is that occasionally you can run into problems where you don't actually have as perfect of a powder as you think you do. There could be stress and strain factors that if you have a powder that's been pressed down in a certain way, you might have accidentally given it a preferred orientation. And that kind of depends a lot on how large the crystal flecks are. If they aren't small enough, then they might have some sort of preferred orientation that's kind of inherent in them already. And that kind of ties in with grain size. If your grains aren't actually small enough, then now you're too close to the original system where you just have a single crystal. So there's kind of a range in which powder diffraction is pretty solid, and there's a range in which maybe anything larger than a few micrometers, you can usually orient that into a single crystal X-ray diffraction experiment. And then also there's some information loss from equivalent reflections. So that ties back into, if we look back at the Miller indices, there are 6 different planes which are associated with, 3 different planes in this case that are associated with a distance of 1, basically. So if A1 equals A2, which equals A3, which it does in this case because this is a cube, then reflections from any one of these planes will be identical. There's no way to tell them apart. So if you come down here, so you kind of lose a little bit of information from that. If A1 does not equal A2, which does not equal A3, then you can perfectly preserve all information about all possible reflections. But in general, cubic kind of loses the most information. And then some other experimental issues that we might run into is absorption effects. X-rays are not perfectly reflected all the time. They can be absorbed by the crystal, and that can cause issues in terms of intensity, meaning that some of the X-rays don't all come out, and if there's a lot of background noise, then you might not be able to get as high of a peak as you want, and it might cause you to have crappy data. And there are also some thermal effects which can come into play. As I said, you want to have elastic scattering, but the thing is, you're assuming that you're elastically scattering off of a rigid crystal structure. If the crystal structure is too hot, then the atoms inside of it are jiggling around. So in a snapshot, you can imagine a photon interacting with a crystal structure is kind of like taking a picture of the crystal structure in one single moment. If the atoms are jiggling around too much, the picture that you're looking at isn't really the true average picture of the crystal structure. It's kind of a warped image where you've got, some atoms which may be slightly to the left or slightly to the right of their sort of average position. And that's brought on by some thermal vibrations. And then finally, there are extinction effects. This is a problem regardless of powder or single crystal. But if you have multiple reflections that are all associated with, like in this case, these are all like the one lattice plane reflection. There we go. And you have a reflection which penetrates really deep into a crystal, or not really deep, this is only 2 or 3 layers deep, and then it starts to come up, and then it's perfectly oriented in a way where it bounces back again. This, some of it will go through the crystal, and some of it will reflect back, and then you end up with sort of this cascading effect where some of them will be transmitted, but some of them won't. So the intensities that you might see may be lower and lower given this sort of extinction phenomenon. All right. So finally, you can see what an actual XRD machine looks like. This one on the left is the one that I use a lot. It's called the Alpha 1. She's my baby. She lives in the Marcus Nanotechnology building. I think Robin.
Are you showing actual pictures right now? Because I can only see the experiment, theoretical. I can see figures, but I can't see an actual picture. Are you showing an actual picture right now?
Yeah. Can anyone else not see it?
We see the experimental apparatus slide.
Yeah.
Experimental. Yeah, this is. Wait. Can you see the? Hold on.
Oh, there we go.
Oh, there
Okay.
it is.
Okay. Were you guys looking at this?
No.
The one before that.
Yeah, that
Yeah.
Did you manage to see this?
No.
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 Did I just point at all these Oh, lads. Lads.
Sorry.
All right. Well, I had figures. I wasn't just like I guess it kind of sounded, like I was rambling as I went through these pictures. But yeah, there was a few things. So yeah, this is the powder effects. This is what I was. Oh yeah, extinction effects don't make sense unless you kind of see this diagram, which is where see, like some get transmitted and then some get reflected and then transmitted and reflected again, and it gets weaker and weaker the more transmission reflections you get. So the intensity can go down because of this, and then there's thermal effects, which shows sort of what it looks like here. You get too much background. All right. Anyways, y'all had your chance. You can come back to that slide later if you want. So this is a picture of some actual X-ray devices. On the left is the Pananalytical Alpha 1. As I said, that's the one I use most of the time. And the one on the right is fancier and prettier, and it has a nice big glass case where you can actually see what's going on. So kind of on the left and on the right, you sort of see this is the X-ray emission arm, and this is the X-ray detection arm. And these two things rotate on this circle and sort of sample over a wide range of angles, and they sort of see what the intensity is at every angle. And that's kind of how you get an idea of the graph we were looking at before of intensity versus theta. Anyways, that's my talk. That was exactly 1 hour, Abel. You're welcome.
Thank you so
went
much.
as fast as I could. Well, here we are. Okay. I'll stick around if anyone has any questions.
Have you talked to Tribino about a bit of this? Because I have a feeling he'd be very interested to like both of you would like to talk to each other.
I mean, I have not spoken to Tribino at any point in my life. I don't think I've only ever seen him, but maybe
He's a very good professor to talk to. You can go on quite a bit, but he always has an interesting conversation.
it's fair. No,
And he knows his optics, so yeah.
Yeah, that makes sense. There's
I
probably.
guess, Charles.
Oh yeah, go ahead, Abel.
So what you guys measure is the intensity for different crystals.
So
That's, like, what is the like the quantity that you guys measure? Like, what is the thing that you guys are interested in?
In
The form
specific,
factor?
where it's the intensity. So
Intensity, okay. For different.
you can tell based on where the intensity, or sorry, where the peak is, meaning the angle that you find it at, and then the intensity, meaning how many photons you're collecting at that angle. That will give you information about the crystal based on the two things that we defined earlier, which is the peak position and the peak intensity. So because you can basically use, where is it? You can use this graph with the intensity and where the position is to reverse engineer the structure factor, and from there the HKL values. And the HKL values basically define your lattice. So if you have a crystal that you don't know anything about and you put it under the XRD and you get this sort of please stop. All right, I got a cat who wants to come up. Give me a moment. All right. And you've got, what was I saying? Where was I? Okay. And you've got
The HKL values for the crystals, I think.
Yes. All right. If you've got your HKL values, you can use them to define your lattice planes. And you can use HKL values to define the coefficients that go along with your reciprocal lattice vectors. And based on that, you've got, if you know your lattice vectors are reciprocal, sorry, I have to put the cat down. Okay. If you have your coefficients of your reciprocal lattice vectors, there basically are your N1, N2, and N3, or in this case, HKL, and you can use them to replicate your entire lattice. As long as you know the what else am I missing? You also need to know the elements which are inside of it, because those will tell you the form factor coefficients. So there are a couple other components. In general, I could show you. 1 second. No? All right, good. Otherwise, she would be laughing at me. So, if you wanted, here, this is going to be real fast and real messy. I just have to load in so, give me a second. No, never mind. Not that one. Oh, there's a cat on my desk and she will not go down. No, stay down. Stay.
Give the cat more
I really
power.
want to meet these legendary cats that you talk about all the time.
They want attention at all points. Okay. So, in general, if you have this, you've got some crystal structure. Or sorry, you've got some intensity versus angle graph. And you say, all right, how the fuck am I supposed to, just out of 2 dimensions, and then also assuming you know what elements make up your crystal, but just out of these 2D and then the elements, how do I figure out what the crystal structure is? You will use a combination of the experimental evidence that you have, meaning the wavelength, the shape of the wave that the photon has as it interacts with the crystal structure, and you can basically define a number of things. So your scale, how large each of these peaks are, A, B, and C, which are basically your reciprocal lattice vectors. This is the coefficients, so H, K, and L, effectively. And then U, V, W, and then usually there's an X down here too. But those are the full width half maximum parameters, which go along with your experimental device. So whatever source of X-rays you're using, they're each going to have unique line shapes, which will be defined in this component. And each of them will also have asymmetries. So you can go through all of this and you can refine different components. And then you could also look at each atom. You could define their X, Y, Z positions. And then you could define all types of other things, whether if there's occupancy differences. Some interesting things about crystals is you assume that just because I tell you this is the unit cell, that every time that you look at a crystal, each unit cell is going to be fully occupied. You might actually have situations where here, there's 2 different ERs located at 2 different, these erbium, 2 different XYZ values, but one of the XYZ values is only half occupied, which basically means that every other crystal, there's only a 50% chance of it being occupied. So just because of the way the crystal forms, you would have some sort of inherent deficiency. That's just a part of the physics inside of it. It's not actually a contamination or anything, but it's just the way that the crystal's formed it only has a 50% chance of existing in the place that it normally would be in the unit cell. And then I can show you. I don't know if there are any other questions or if that actually answered the question you were trying to ask. That's not what you wanted about?
Yes,
okay.
That's what I wanted.
Okay. I was going to say, if you want to, you can also just look at a crystal structure. It can pull up all the stuff you... Oh, go ahead.
I had a question
Matt.
about the lattice vectors that you talked about at the beginning. So were those the N1 and N2, were those like, did that like index the lattice? Is that what the purpose of those are? Okay.
So yeah, if you have some sort of Bravais lattice defined in this way, N1 and N2 can only be integer values. So if my origin's here and then N1 equals 1 and N2 equals 0, then that means I have R equals just 1 times A1, and that will get me from my origin to here, and then I could keep doing that repeatedly to define a line, and then if I have like N2 equals 2, N1 equals 0, then I could go here to here to here, so on. So yeah,
Okay.
those they define every point on your lattice.
Gotcha.
So it seems like group theory is like very advantageous for studying these kind of systems.
Oh yeah, as long if systems are periodic, then like holy shit, it makes a lot of things easier.
Yeah.
It is. So there's also like there's even types of like protein crystallography where they'll take something which isn't like a biological sample that isn't crystallographic in any way, and they will like force it to enter a crystalline state, like a pseudo-crystalline state, so that they can do XRD on it to understand the protein structure. Because proteins are really difficult to like characterize, and they're very complicated, and they're literally like almost a micrometer long. And actually, no, that feels too long. I don't know. They're big. They're ask Gumbart. They're hard. and you can use XRD on them to help characterize them. Not all of them, obviously, but in some specific cases. All right. Anyone else? Who's Liam Ford? I've never seen this person before.
I think he's a first year.
Welcome, Liam.
He's in our GT1000 class.
Well, Tony just came in.
My lad, Tony!
What do you
I gotta go, guys, but that was a great talk.
Oh, thank you, Nadia. I'll catch you around.
Catch you
I
later.
agree. Good talk. Thank you very much.
Thank
God
you,
bless.
Liam. God bless.
Alright, I'll stop